Hello everyone, good evening. Welcome to the second week of the live interactive sessions for concrete technology. My name is Sedu Vinayagam. I am a PhD scholar in the Civil Engineering Department at IIT Madras. Okay, so we'll get started with this session. So first we'll start with an overview of the lectures covered in week 2. So again we had 3 lectures in week 2. So in the first lecture of this week, which is the 4th overall, we continued with the porosity of cement paste, right? So this was discussed in week 1 as well, but continued in week 2, right? So we looked at again the porosity, how to calculate the porosity of cement paste. So what are the from where the porosity is coming, right? One, there is porosity in the cement gel, right? So in the cement paste as hydration takes place, and there is also capillary porosity, right? So we have so water takes up some volume, right, in the concrete, and with time, as hydration occurs, so this space that was originally occupied by water will be filled by the hydrated products, and then some of the volume that was occupied by the water earlier will still remain empty, right? So that is the capillary porosity, right? So that is with respect to the porosity of cement. Then we looked at different properties of cement, like setting time, fineness, soundness, and strength, and what are the tests that we perform on cement to determine these different properties. So that was covered in lecture 4. And then in lecture 5 we looked at different types of cement, right? So so in the first week we were not talking about different types, we are only looking at cement in general, so mainly OPC. So here different types of cements were introduced, right? How we modify the different how we modify cement, right? How do we enhance certain properties to suit certain applications, right? And therefore results in different types of cement. And then we looked at lime, right, and the types and then the reactions that takes place with lime. And we also looked at different supplementary materials that could be used in the production of cement, right? So like fly ash, slag, silica fume, right? So we add these materials as supplementary materials, right? So we replace some proportion of the cement with these materials to get better durability, better enhanced performance, and so on. And in the final lecture of week 2, we moved on to aggregates, right? So it was the start of module 2. So we looked at aggregates and what is the requirements of an aggregate should satisfy for use in concrete. And then what is the petrographic classification, right? So based on the chemical composition, right? How do we classify aggregates? And then also we looked at aggregate size, shape, and texture, and so what are the different sizes, shapes, and textures that how do we classify aggregates based on these properties, right? So that was what was covered in week 2. And now we will look at some questions that are related to these concepts that were covered. So the first question is, what is the cement to sand ratio for testing of mortar cubes for strength? So the options are 1:1, 1:2, 1:3, and 1:4. So as usual, I'll create a poll and then you can respond to the poll. Okay, I have launched a poll. Once you are ready with your answer, you can answer in the poll. Okay, we have a couple of votes for option C. Any other answers before we move? Okay, so let's take a look at the answer now. So the right answer is option C. The ratio we use is 1:3, right? So if the standard that talks about the strength test, right, for concrete, so it is IS 4031 part 6, which is about determination of compressive strength of the hydraulic cement other than masonry cement, right? So this is what we are concerned with, hydraulic cement. And for the compressive strength test, so this is the standard that we use, and that standard says the specimens that we prepare for this strength test, it will be cube specimens of size 70.6 mm, right? So that is around 7 centimeters, and it should be prepared by mixing 200 grams of cement with 600 grams of standard sand, right? So this is what the code specifies. So if you look at it, 200 grams of cement should be mixed with 600 grams of sand. So that is in the ratio of 1:3, right? So the question was about cement to sand ratio, right? So 200 to 600, so that is 1:3, right? So that's why the answer is C, 1:3. Okay, so question number 2, which of the following is the characteristic of sulfate resisting cement? The options are low C3S, low C2S, low C3A, and low C4AF. Okay, the poll is launched. You can answer in the poll. have mixed response. One vote each for A, C, and D. Any other answer? Okay, so let's take a look at the answer now. So the right answer is actually C3A, right? So low C3A. So in sulfate resisting cement, the C3A content will be lower, right? So if you remember the slide from the lecture, so type 5, ASTM type 5 is what is the low or the sulfate resisting cement, right? So in that, if you look at it among all the different compounds, the content of C3A is the least with respect to type 1 is the OPC, right? So with respect to that, if you see, the C3A content is much lower, right? But why do we reduce the C3A content? Right, so remember from week 1, so we discussed about heat of hydration, right? So C3A has the highest heat of hydration, so that means that it reacts quickly, it reacts faster than say C3S and C2S, right? So what happens, so when C3A reacts so quickly, the hydration will be completed by C3A itself, and then there won't then it does not allow C3S and C2S to completely complete the hydration process. So but that is not desirable, because C3S and C2S is what are responsible for the strength development in concrete, right? So to reduce that, what do we do? In general, we add gypsum, so that the C3A will so the setting of cement will be delayed, right? So because C3A will combine with gypsum to form the ettringite, right? So that's what we generally do. So what happens when we talk about sulfate resisting cement, right? It is used to counter sulfate attack. So in environments where we encounter sulfate ions to react with the cement, right? So in those cases, what will happen is this sulfate attack happens, where the sulfate ions will also produce ettringite. So when it reacts with carbon hydroxide, right? And what is the problem with more formation of ettringite is that it leads to expansion of concrete, right? So the volume will increase largely, right? So because of that, there will be more tension developed, and then it leads to cracking of the concrete, right? So to counter that, we reduce the amount of C3A that is present in the cement, so that this expansion or the sulfate attack can be prevented, right? That's why in sulfate resisting cements, we reduce the C3A amount. Okay, so any questions before we move on? Okay, so moving on to question number 3. Which of the following is not a supplementary cementitious material for cement? The options are fly ash, sand, slag, silica fume. Okay, so we have 2 votes for option B, sand, and 1 vote for D. Okay, let's look at the answer. So the right answer is option B, sand, right? So the question is, which is not a supplementary cementitious material for cement, right? So we can use fly ash, slag, as well as silica fume as supplementary materials, right? So we can use that to replace some proportion of cement, right? So to modify its or enhance its properties, right? But we don't use sand as a supplementary material, right? So these are called pozzolana materials, right? So they react, they also can react with lime in order to produce the CSH gel, right? And therefore they can be used as cement supplements. So if you look at fly ash, it is obtained as a result of the processes from the thermal power plants. GGBFS, or the slag represented here, it is the granulated slag, that blast furnace slag that we obtain. And then silica fume it is also from the silicon industry. So all these can react with lime to produce the CSH gel, which is what cement will also produce, right? So therefore they can be used as a supplementary material. So in addition to this, there is also rice husk which can be used, right? So this is one type of supplementary material, right? So like we call these as mineral admixtures, right? But sand is not a supplement for cement. Okay, so question 4. A cement paste prepared with 400 grams of cement has a water to cement ratio of 0.42. What is the capillary porosity at the end of 1 year, assuming that maximum hydration has taken place? The options are 0, 0.25, 0.5, and 0.75. Right, so the question is, you have to find out the capillary porosity given that the water to cement ratio is 0.42 after hydration has completed for 1 year, right? So assume that maximum hydration has happened. Okay, we have only two answers so far. I'll just wait for 1 or 2 more minutes. Okay, so we have a couple of votes for option A, 0, and one vote for option C, 0.5. So let's take a look at the answer now. Right, so the right answer is option A, 0. Right, so when so there will be no pores left, right? So let's look at how we arrive at this answer. So what do we need to calculate is the capillary porosity, right? So by definition, what is this? This is nothing but the volume of capillary pores divided by total volume, right? So this is by definition what is porosity, right? So we need to know the volume of the capillary pores and total volume. With that we will be able to get the capillary porosity. So so what is the volume of capillary pores? So if you remember from the derivation that was performed in the class, so it was W minus 0.36 CH, right? So where W is the volume of water that is reacting, and then C is the mass of cement, that is initial mass of cement that is taken, and H is the degree of hydration, right? So with that we'll be able to get the volume of capillary pores, and the total volume is nothing but, so we have C grams of cement, so C by 3.15 plus W, right? So this is the total initial volume, right? So C grams of cement, so 3.15 is the specific gravity. So from that we get the volume of cement, and W grams of water if it is there, so WCC. So the total volume is given by this, right? So this is capillary porosity. But what is given in the question? In the question it is said that maximum hydration has taken place, right? So we have to assume that complete and maximum hydration has taken place. So what happens at maximum hydration? So at maximum hydration the porosity will be 0, right? So porosity is 0 because when complete and total hydration is completed, so all the pores will be filled, there won't be any capillary pores that will be left, right? So at maximum hydration the porosity will become 0, right? So what does that mean? If porosity is 0, then the volume of capillary pores should be 0, right? So if you equate this capillary porosity to 0, which means that the numerator should be 0, right? So then only porosity will be 0 because initial volume is not 0. So W minus 0.36 CH right? Given that it is the maximum hydration, which we'll call it as H max. Okay, let's call that as H max. So this should be 0, right, at maximum hydration. So from this, if we find out what we can get is H max is, so if you just rearrange the terms here, we'll get H max is nothing but W by C divided by 0.36. So what does this tell us? So what is H max? It is the maximum degree of hydration, right? So it can be at most 1, right? So which means that all the cement that we have taken has hydrated. So if your W by C is greater than 0.36, which means that there is enough water that is left, that is present for the maximum hydration to take place. Whereas if your W by C is lesser than 0.36, then the maximum hydration that can happen will be less than 1, right? So now we have to know what is the W by C, so that we know what is the maximum hydration that is possible. So in the question it is given that the water to cement ratio is 0.42, right? So if we compare that here, we have we know that it is greater than 0.36, right? So 0.42 is the current water by cement ratio, but at 0.36 itself is enough to achieve complete hydration, right? So for 0.42, H max is 1. So which means that all the cement is hydrated, so therefore the capillary porosity will be 0, right? So when W by C is greater than 0.36, H max is equal to 1, right? So complete hydration will take place, so there will be no pores left. That's why the answer is 0. Okay, any questions? Okay, so if there are no questions, we'll move on to question number 5. So question 5, a cement paste was prepared with 300 grams of cement and a water to cement ratio of 0.3. So calculate the volume of gel pores in cm cube units at the end of 1 year, assuming that maximum hydration has taken place in 1 year. Yeah, if you have any doubts, you can unmute yourself and ask, or ask in the chat box. So there's no option, you can put your answer in the chat as well. You can type your answer in the chat. Okay, any answers? Okay, we have one answer, 0. Alright. Anyone else? So I think we can look at the answer now. So what is the question? The question is to calculate the volume of gel pores, right? So volume of gel pores is given by 0.19 ch, right? So again, this is from the porosity calculations. So we know that the volume of gel pores is 0.19 ch, where c is the mass of cement and h is the degree of hydration, right? So to get to know the volume of gel pores, we need two quantities. One is what is the mass of cement and what is the degree of hydration. From the question, we know what is the mass of cement, right? So c is known. So we need to know the degree of hydration, only then we can get the volume of gel pores. So what is the information that we are given with? So we are given with the water to cement ratio, which is 0.3, and we are also told that that maximum hydration has taken place in 1 year, right? So those are the two pieces of information that we have to get to find out what is the degree of hydration. So from the previous question, we arrived at this equation, right? So for a given water to cement ratio, what is the maximum degree of hydration, right? So that, what was that relation? So it was W by C by 0.36, right? So this is what we saw derived in the solution for previous question, right? So for a given water to cement ratio, the maximum degree of hydration is given by this relationship, right? So now in our problem, the degree of water to cement ratio is 0.3, right? So 0.3 by 0.36, that will give us the ratio as 0.83, right? So which means that the maximum hydration that can take place is only 83%, right? So which means that if C grams we are taking, only 0.83 C will form the hydration products, right? So for this particular water to cement ratio, and therefore at maximum hydration, the volume of gel pores at maximum hydration is nothing but 0.19 times C, which is 300 grams, times the maximum degree of hydration, which is 0.83, right? So this, if you calculate it, it will be coming around 47 I think 31, right? 47.31 centimeter cube, right? So that is the volume of gel pores that will be present when maximum hydration has taken place, right? So when 300 grams with the water to cement ratio of 0.3 hydrates at maximum hydration, after maximum hydration has taken place, there will be 47.31 centimeter cubes of gel pores remaining, right? Any questions? So this, we are using the concept that we learned in the previous question, right? So for a given Hmax, we know the relation between Hmax and the W by C, right? So we are using that relationship to determine what will be the maximum degree of hydration, and then using that to get the volume of gel pores, right? So the answer is 47.31. Okay, so if there is no doubt, we will move on. Question 6. So choose the correct match from the following of the following properties of cement with the apparatus used for their testing. So we have listed 3 different properties: consistency, soundness, and specific gravity. And we have 3 apparatus given here: Le-Chatelier flask, Le-Chatelier apparatus, and Vicat's apparatus. So we have to match which test is performed using which apparatus. Okay, so 4 options are given. So which of these options represent the correct matching? Okay, so let me create a poll. Any answers? Okay, there is only one vote so far for option C. Anybody wants to try? before we look at the answer. Okay, so let's look at the answer now. So the right answer is option B, right? 1 with 3, 2 with 2, 3 with 1, which is standard consistency is tested using the Vicats apparatus. Soundness is tested using Le Chatelier apparatus, and for specific gravity we use the Le Chatelier's flask, right? So if you remember the tests that that was covered in the lecture, so you'll remember the apparatus that we use for the different tests, right? So it's just a matter of remembering which is the apparatus that we use to do the different to test for different properties. Right, so the correct match is option B. Okay, so question 7. So here we are moving on to aggregates. So if the mean sieve size is 8 mm, so what sized particles will be considered as elongated? Right, so the options are having thickness less than 4.8 mm, having thickness more than 4.8 mm, having length more than 14.4 mm, having length less than 14.4 mm. So what is the criteria that we use to say that a aggregate is elongated or not? Okay, any answers? I can give you a hint that it has to do with length and not the thickness. So that eliminates two options.
వాడు హెచ్చుండలేదా?
Okay, so we have two answers so far, one for option B, one for option C. Any more answers before we move on? Okay, so let's take a look at the correct option now. So the right option is option C, having a length more than 14.4 mm. So how did we get this 14.4? So the criteria is that a particle is elongated if its length is more than 1.8 times the mean sieve size. Okay, so the mean sieve size that we are given is 8 mm, right? So if you calculate 1.8 times 8 is 14.4, right? So if a particle has its length more than this 14.4 mm, then we call that as elongated particle, right? So that is the criteria, right? So this is what we use, 1.8 times the mean sieve size. Okay. Okay, so moving on to question number 8. Which of the following represents the true relation between void content and angularity factor? So the options are: void content is unrelated to the angularity factor, void content decreases with decrease in angularity factor, void content increases with decrease in angularity factor. Option D is none of the above. Okay, there is one answer for option B. So for others who join late, there is a poll going on after each question, so you will find it within the activities option and you can answer in the poll. Okay, two answers for option B. Okay, so let's take a look at the answer now. So the right answer is option B. Void content decreases with a decrease in the angularity factor, right? So before we understand why that is the true relation, so we need to know what angularity factor is, right? So it is, angularity factor is defined as the reciprocal of the sphericity factor, right? But what is sphericity factor? So sphericity factor is nothing but the ratio of the specific surface diameter to the volume diameter. So what it means that the sphericity factor will be higher if the particle is more spherical, right? So if it is less irregular and more spherical, the sphericity factor will be higher, or the angularity factor will be lower. So if the angularity factor is higher, it means that the particles are more irregular, right? So that's what it means. So angularity factor is nothing but it is related to the how irregular a particle's shape is. Okay, so higher angularity means more irregular the shape is, right? But how it is related to the void content? So for that we know that spherical particles gives us the highest packing density, right? So when the packing density is higher, the voids will be lower, right? So the particles are more spherical, the voids will be lower, right? Packing density will be higher. So which means that in other way we can say it as, if the particles are more irregular, then the void content will be higher, right? So that's the other way of saying it. So which means that the void content will increase if the angularity factor increases, right? So here option B is looking at it in the reverse way. Void content decreases with decrease in angularity factor, right? So we also have this graph which represents that relationship, right? So as the angularity factor is higher, the void content is also higher, right? So that is the relation that we have, right? So which we can also say it as void content reduces when the angularity factor reduces, right? So B is the correct relationship. Any questions? So just what do you take away from this is that spheres give us the highest packing density, least void content. The more irregular the aggregates are, the more voids that will be created. Okay. So question number 9. Which of the following is correct with respect to rapid hardening Portland cement or the ASTM type 3 cement? The options are, it has low C3S and low C3A. Option B is it has high C3S and low C3A. Option C, high C3S and high C3A. Option D is low C3S and high C3A. couple of votes for option D, low C3S, high C3A, and one answer for option A, low C3S and low C3A. Okay, any other answers? Okay, let's take a look at the answer now. So the right answer is actually option C. Both C3S as well as C3A are higher in the rapid hardening cement. So we said it is type 3, right? ASTM type 3 is a rapid hardening cement. So if you look at it, you compare it with OPC, which is our type 1. So it has higher C3S as well as higher C3A, right? So it is higher in proportion. But why do we have these two higher? So remember, this is a rapid hardening cement. So what do we mean by rapid hardening? It has to set quickly, right? So if you remember again from our previous week, we said, right, C3A affects the setting property, right? The setting is affected by the amount of C3A that you have, right? So it has the highest reactivity. So when you have higher C3A, you have quick setting, right? It will hydrate faster. But it is not necessary to just set, right? You also need strength development, right? So early strength is also needed, right? Just setting is not enough. So strength is given by what? C3S as well as C2S, right? So we know that. But among these two, it is C3S which is responsible for early strength development, right? So that's why we have higher C3S, right, which gives us higher early strength, as well as higher C3A, which affects the setting, right? So that's why in the rapid hardening cement we have higher C3S and higher C3A. Okay, any questions? Okay, so moving on to question number 10. Similar to what we saw earlier, but here we are talking about flaky particles instead of elongated. So if the mean sieve size is 8 mm, so what is the particle size that will be considered as flaky? So the same option as we had earlier, having a thickness less than 4.8 mm, having thickness more than 4.8 mm, length more than 14.4 mm, and length less than 14.4 mm. So what's the criteria to say that a particle is flaky or not? Poll is launched. You can answer in the poll. saw that elongation has to do with length. So similarly, flakiness, the thickness determines whether a particle is flaky or not, right? So that's the hint. So we have two answers so far, one for option A, one for option B. So do we have any other answers? Okay, so let's take a look at the answer now. So the right option is option A. When the thickness of the particle is less than 4.8 mm, then it will be flaky, right? So this is for a given mean sieve size, right? So actually the criteria is we call a particle as flaky if the thickness is less than 0.6 times the mean sieve size, right? In our case, the mean sieve size is 8 mm, right? So 0.6 times 8 mm is 4.8 mm, right? So that's why we compare the thickness, and if the thickness is less than 4.8, then we call that particle as flaky, right? So the actual criteria is 0.6 times the mean sieve size. So thickness, if it is less than that, it is flaky. Okay, so question number 11. So we have four statements here. So first statement is expansive cement used in grouting has high alumina content. Statement 2, low heat cements are preferred for construction of dams. Statement 3 is the long-term strength of low heat cements is lower as compared to ordinary Portland cement. Statement 4 is sulfate resisting cements has high amount of alumina. So we need to find out which of these statements are true. So we have four options. Statements 1 and 3 are true. Option B is statements 2 and 3 are true. C is statements 1 and 2 are true. And option D is statements 2 and 4 are true. So just think about each statement and determine whether it is correct or not.
అప్పు ఎంత తెలిసి కట్టుకుంటాము.
please answer in the poll. We have only one vote so far for option C. Okay, any other answers other than option C that we have here? Okay, so let's take a look at the answer now. So the right option is option C, statements 1 and 2, right? So only statements 1 and 2 are the correct statements. So why is that? So let's look at the incorrect statements first, so which is 3 and 4. So statement 4 we already talked about sulfate resisting cement, right? So we started, so one of the first questions was about the sulfate resisting cement, and we saw that in the sulfate resisting cement we have lower C3A, right, as compared to OPC. And why is that? Because we wanted to prevent sulfate attack, where in a sulfate attack the volume increases because of a large formation of the ettringite because of the reaction of this sulfate ions, right? So to counter that, we reduce the amount of alumina in terms of the compound C3A, right? So that's what we do in a sulfate resisting cement. So this statement says that sulfate resisting cement has high alumina, right? But that is just opposite of what we do in a sulfate resisting cement, and therefore that's an incorrect statement. And statement 3 is long-term strength of low heat cement is lower as compared to an ordinary Portland cement. So if you again remember what is how this low heat cement compares with OPC, is that in low heat cement we have lower C3S but higher C2S as compared to OPC, right? And between C3S and C2S, if you remember, C3S is responsible for the early strength development, and C2S is responsible for the long-term strength, right? So when C3S is lower and C2S is higher in comparison to OPC, what will happen? The long-term strength will actually be higher for the low heat cements, right? But this statement says the opposite, that low heat cement have a lower long-term strength than OPC. Therefore, that is incorrect, right? So it is the opposite. Early strength will be lower, but the long-term strength will be higher for low heat cements. So that's why statements 3 and 4 are wrong. So the correct statements are 1 and 2. So statement 1 is expansive cement used in grouting has high alumina content. Like, so this is just like the opposite of statement 4. In statement 4, we are trying to prevent this excess rise in volume because of the sulfate attack, right? Where we want to prevent that. Whereas in applications where we need this expansive property, right? So for example, in filling, in crack filling repairs, where we need this property, as the name suggests, it is expansive. So we need a higher alumina content, right? Just the opposite of what we needed in a sulfate attack situation. We just need the opposite of that, in applications where expensive cement is used. Therefore, it needs to have high alumina content, right? That's why statement 1 is true. Statement 2, it is about low heat cement. So low heat cements are preferred for construction of dams, right? So that is also true. Not just in dams, any mass construction where we have higher volume per unit surface area that is exposed to the atmosphere. So in that cases, we prefer low heat cement, because when you have a lot of heat coming from the hydration, if it is not getting dissipated to the atmosphere, right? So when so for example, in the construction of dams, so we have lesser surface that is being exposed in comparison to the volume that is not exposed, right? So there will be a higher heat that will be generated, and if this is not going to be dissipated, then there is going to be a differential of heat, right? So there will be, it's going to be more hot inside the dam than it is outside, right? So this heat differential can cause cracking, right? It can lead to cracking in the dams, right? So we don't want that to happen. Therefore, we go for a low heat cement. So right, so let's we try to address it by reducing the amount of heat that is generated in the first place, right? Because we know there is the dissipation is going to be lower, so we go try to compensate that by reducing the heat that is generated, right? So to do that, we go for low heat cements, right? That's why statement 2 is correct, right? So so out of the 4, 1 and 2 are correct and 3 and 4 are incorrect. So that's why the correct option is option C. Okay, any questions? Okay, so moving on to question number 12. Which of the following is not a characteristic of RHPC, which is rapid hardening Portland cement, compared to OPC? So options are high early strength, option B high long-term strength, option C it enables early removal of formwork, option D is high fineness of cement. So we are comparing RHPC with OPC.
Or high long-term strength.
Okay, let's just wait for others also to answer. You can make use of the poll, it will be easier to see the distribution. Okay, do we have any other answers? For people who joined late, we have a poll for each question, so you can put your answer in the poll. Okay, so we have 2 votes so far, one for option A, one for option B. So high early strength and high long term strength. So let's look at the correct answer now. So the right option is option B, high long term strength. Right, so what are we saying is RHPC has lower long term strength in comparison to OPC, right? So that's what we mean. So the question was, which of the following is not a characteristic of RHPC as compared to OPC? So in comparison to OPC, RHPC has high early strength, it enables early removal of formwork, and it has high fineness. So why is that? So we saw, as the name suggests, it's rapid hardening, right? It will set quickly, it will harden quickly. So in comparison to OPC, so when that happens, it is we can remove the formwork early, right? Because it sets quickly, and it also has high fineness, right? So again, remember, the more is the surface area, right, more will be the higher will be the reactivity, right? So how do we get more surface area? When the particles are finer, the surface area will be larger, right? So therefore that enables quick reactions, right? Therefore high fineness is also a characteristic of RHPC. And we also saw that in RHPC we also need high early strength development, right? It's not just setting, but we also need quick strength, right? So for that, high early strength is also its characteristic, right? So we have higher C3S and lower C2S in comparison to OPC. So when C2S is lower, its long term strength is going to be lower than OPC, right? So that's why option B is incorrect. That is, it is not a characteristic, right? It's correct for this question, but in comparison of RHPC and OPC, that is the incorrect statement, right? So it has a lower long term strength. That's why option B is correct as being not a characteristic of RHPC. Okay, any question? So RHPC has high early strength, it enables early removal, and it also has high fineness, but it does not have a high long term strength in comparison to OPC. Okay, so moving on to question number 13. What is the angularity number for the most rounded aggregate? So options are 67, 100, 35 and 0.
Zero, sir.
Okay, so let's wait for other answers. Yeah, please use the poll. Okay, any other answers? Okay, so we have 2 votes for option D 0. So let's look at the correct option. So the correct option is option D 0. So why is that? So how do we calculate the angularity number? So the angularity number is nothing but 67 minus the percentage of the solid volume when you fill the particles in a vessel, right? So that's the formula for calculating the angularity number. So when the question was about the most rounded aggregates, for most rounded aggregates this percentage is nothing but 67, right? So the difference of 67 minus 67 comes out to be 0. So which means that the angularity number, so it like the most rounded aggregates have is like our baseline, right? So with respect to that, how much the irregular shapes will have, that's what we can get out of this angularity number, right? So if that number is higher, which means that they are less spherical or more irregular, right? So that's what we get it from the angularity number. So because the most rounded aggregates are like our baseline, so this number is 0, right? So anything greater than that, it will be less spherical or more irregular. Okay, that's why it is 0 for the most rounded aggregates. Okay, so question 14, we have to compute the specific surface diameter of a given aggregate particle which has a cubical shape of side A, right? So the options are A squared, 1 by A and 6A squared.
Six A square D.
Okay, so let me just launch the poll. You can put your answer in that and we'll wait for others also. Okay, so we have a couple of votes for option D, 6a square, one for option C, A. We'll just wait for 1 or 2 more minutes. Okay, any other answers? Okay, so let's take a look at the correct option now. So the right option is actually option C, A, right? It's not 6a squared, it's A. So, but how do we get it? So before that, so let's see what we mean by the specific surface diameter. Okay, the specific, so the definition is nothing but the specific surface diameter is the diameter of a sphere of equivalent you know surface area, specific surface area as the irregular particle, right? So we are dealing with a particle with an irregular shape. So in our case it is a cube, right? So but we want to find the diameter of a sphere which has a similar specific surface area or an equal specific surface area as this irregular particle, right? So that's what we need to find out. So to do that, what do we need? We need to find the specific surface of this irregular particle. And what is the or how do we calculate the specific surface area? So the specific surface area is nothing but the area of the particle, if it is A, let's call that AP, to per unit volume, right? So the area per unit volume, that gives us the specific surface area, right? So for a given particle, based on its shape, we can calculate what its area is, what its volume is, and we need to equate that to that of the sphere, right? So we need to know what is the specific surface area for a sphere. So the specific surface area of sphere is nothing but we need to divide the area of the sphere by its volume. So for area it will be pi d square if d is its diameter, right? And volume will be 1 by 6 pi d cubed, right? So that if you just simplify it, you will get it as 6 by d, right? So that is the specific surface area of the sphere. So in our question, so we are dealing with a cubical particle, a cubical shaped particle. So we need to find, so its area and its volume, if we equate, if you use that to calculate its specific surface area and equate it to 6 by d, you just have to find what is the value of d, right? So that's the question. Okay, so for so let's say 6 by d, so that's for the sphere. So we need to equate that to that of the cube. So for cube, the area will be what? 6 a squared, right? So for one side it is a square, we will have 6 sides, so 6a squared. So the volume will be a cubed. Okay, so from this you can find that so 6 will get cancelled on both sides, a squared and a cubed, so a will be remaining. So finally you will find that d is equal to a, right? If you just simplify that, so that tells us the specific surface diameter for a cubical shaped particle is nothing but its side length a. Okay, so what we have done is we have just used the definition of a specific surface diameter, right? So we know that it is the diameter of an equivalent sphere that has a similar specific surface area. So for a sphere we calculated it by taking the ratio of its area to volume, so that came out to be 6 by d. So similarly we calculated that for a cube, which is 6a square by a cube, and by equating that, because we are talking about equivalent particles, right, of same specific area, so we equated that to find out what d is in terms of a, right? So it's just nothing but d is equal to a. So that's why the option C is correct. Okay, any doubts why it is a? So we are not talking about the area of this cubical particle, right? So in that case it will be 6a squared. We are talking about the specific surface diameter, so it has to do with an equivalent sphere. Okay, so that's how we do it. Is it clear? Any questions? Okay, so let's move on. Question number 15. So void content in aggregates depends on the following, which of the following characteristic? Options are shape of the aggregate, size distribution of the particles, the packing characteristics, and option D is all of the above.
All of the above.
Okay, let's wait for other answers as well. Okay, there is one doubt. How is the volume calculated in the previous question? Right, so we have two different shapes that we are dealing with, right, in this question. So one is the sphere. So we just so we don't know the diameter, so we just take the diameter to be d, right? So for some diameter d, so the volume for the sphere is nothing but 1 by 6 pi d cube, right? So that is for the sphere. The other shape that we are dealing with is nothing but the cube. So this it is given that the side length of the cube is a, right? So if the side length is a, the volume of a cube is nothing but a cubed, right? So based on the shapes, the volumes will change, right, in terms of their dimensions. So we take the dimension of the sphere to be d, and the shape dimension for the cube is given as a. So using that we get the volumes as a cubed and 1 by 6 pi d cube for the cube and the sphere. Okay, so any other questions? Okay, so yeah, so question 15 you can answer in the poll. So a couple of votes are already there for option D. Right, so we have more option D's. Okay, any other answers? Okay, so let's take a look at the right option. So it is in fact option D, all of the above, right? So the void content will determine based on the shape of the aggregate. So we already saw this, right? So the packing density is influenced by the shape, right? So if it is spherical, so then we get the most packing density, which also gives us with the least voids, right? So the shape matters. The more irregular, there will be more um, voids. The size distribution will also matter, right? So when you have different sized particles, so the voids created by the larger sized particles can be filled by smaller sized particles, right? So the smaller sized particles can help reduce the voids created by the larger size. So similarly, the voids created by those smaller sized particles can be filled by even smaller sized particles. So if we have a large or a varied distribution of sizes, then also the voids created by one size of particles can be filled by another size, right? So it also affects the void content of your the aggregates, and the packing characteristic also, right? If the packing density is higher, your void content is going to go lower, right? So the packing characteristic will also affect your void content. So the right option is all of the above. So question 16, again related to void content, but in terms of the angularity factor. So how is the void content related to the angularity factor? Options are linear, quadratic, exponential. Option D remains constant. Okay, in fact I showed the graph in one of the earlier questions, if you remember, then it is easy. So what is the nature of the relationship between the void content and the angularity factor? Yeah, please make use of the poll for answering. Okay, we have a couple of votes for option A. Any other answers? Okay, so let's take a look at the correct option now. The correct option is option A. It varies linearly, right? So we saw that angularity factor uh, is related to how irregular a particle is, right? So if the angularity factor is higher, the more irregular is the shape of the particle, right? So more irregularity means there will be more voids right? Because we know that for the spherical shape we have the least amount of voids, or the most higher packing density compared to an irregular shape. So we know that it increases, but the nature of this increase of the void content with angularity factor is it is linear, right? Which means that for every unit increase in your angularity factor, there will be a constant increase in your void content, right? So that's what the linear relationship means, right? So it doesn't matter whether you go from 1.5 to 2 or you go from 1 to 1.5, the amount of increase in your void content will be the same, right, irrespective of where you start from, right? So that's what the linear relationship means, right? And for void content and angularity factor, the relationship is linear. Okay, so question number 17. So we have two statements. OPC, statement 1 is OPC has a high amount of calcium oxide and a low amount of silica. Statement 2 is pozzolana have a high amount of calcium oxide and a low amount of silica. So we have four options. Only statement 1 is correct, only statement 2 is correct, both these statements are correct, and neither statement is correct. So we are comparing OPC and pozzolana in terms of their calcium oxide and silica content. Okay, both statements are correct. We'll see. One more answer saying option A, only statement 1 is correct. Okay, any other answers? Okay. Okay, so let's take a look at the right option now. So the correct option among the four is option A. Only the first statement is correct, whereas statement 2 is not correct. So remember this diagram. So this tells us the how the chemical composition is different among the three different materials. One is the cement, another one is slag, and the pozzolana, right? So O represents Portland cement, S for slag, and P for pozzolana. And if you look at this triangle, so the three vertices are nothing but, so this vertex CaO is 100%, so there is 100% CaO, there is 100% Al2O3 and 100% SiO2, right? So if you compare, so in this question we are looking at OPC and pozzolana, right? So O and P, that is what is of interest to us. So when you look at OPC, so there is high CaO, so we are towards this vertex, so where 100% CaO is there, so there is a high content of CaO. And the other one we are talking about is silica, so which is this vertex. So this vertex is 100% silica, whereas here it is 0%, right? So the silica content is lower, but CaO is higher in terms of for OPC. Whereas if you look at pozzolana, it is higher, it has higher SiO2, but CaO is lower, right? So CaO is much lower than OPC, right? So Al2O3 is also lower, it is high in silica for pozzolana, whereas for OPC it is high in calcium oxide and not in silica, right? So if you look at the statements, both are talking about calcium oxide and silica, both are saying high amount of calcium and low amount of silica, but it is true only for OPC, right? So OPC has high calcium oxide, low silica, right? So only that statement is correct, right? So the right option is option A, right? Any questions? Okay, so this is the last question for this week, right? So if you have any further doubts, you can ask. Otherwise, we'll stop the session here and continue next week. Okay, we'll meet again next Tuesday at 6 p.m. Okay, so I'll just stay back for a couple of minutes in case you have any questions. So if you have no questions, you can feel free to leave the session. Thank you. Okay, so this triangle is just telling us about the composition of three different compounds, right? So one is calcium oxide, so other is Al2O3 and SiO2. So those three compounds represent are along the three directions. So if we look at it, so this vertex leftmost, it's for CaO, where the composition of CaO is 100%, right? So if you have 100% CaO in a particular material, so then it will be lying on this over this particular vertex where CaO is 100, right? Whereas the other direction, it will keep on reducing the CaO composition, so it is 100% here, 0% here. So similarly for Al2O3, this vertex represents 100% of Al2O3, right? So in this direction if you go, Al2O3 composition is reducing. Similarly for SiO2, this vertex represents 100%, and if you go in the opposite direction, it will, and the composition of SiO2 is lower, right? So that is how it is arranged. So and then we see within this triangle where a particular material is falling, that will tell us what is the composition of these three compounds in that material, right? So if you look at O, which represents a Portland cement, it is lying here, which is closer to this vertex, right? So which means that it has a very high concentration of high composition of CaO in it, whereas it is very far away from the SiO2 vertex and Al2O3 vertex, right? So which means it has comparatively lower SiO2 and lower Al2O3 in comparison to CaO. Whereas the other one in question is the pozzolana, so where it is lying here in the triangle, which has a lower CaO content, so it is away from that vertex, whereas it is closer to this vertex, which represent it is very high in silica, right? So that's why CaO is higher in O and low in SiO2, whereas for pozzolana it is high in SiO2 and low in CaO. So which means that statement 2 is wrong and statement 1 is right. Okay, is that clear how we look at the triangle? No, For slag, CaO, I would say CaO is slightly higher than SiO2. So it's more closer to CaO than SiO2, right? So it is slightly higher. CaO is slightly higher in slag than SiO2. Okay, any other questions? Okay, if there are no further questions, so we'll stop the session here. We'll continue again next week. Okay, thank you.
Thank you.